Okay. Last day we have discussed Gram-Smith orthogonalization procedure. You people need to practice those things, otherwise it will be difficult to solve the numerical. Okay, so you practice it. If you have any doubt, you can ask. Because Gram-Smith orthogonalization procedure is not difficult, but some steps are there, some process you should know, some basic concepts are required of the subtractions of signals and multiplication of signals. These two concepts is very important for GSOP. Okay, so today we are going to start the new topic, which is your probability of bit error analysis. Probability of bit error analysis for any digital modulation technique. So here we are going to consider for the case of binary phase shift key. For this BPSK, we will calculate the probability of error or probability of bit error. Okay. So how to calculate? What is the procedure to calculate probability of bit error? Very interesting. Okay. See, before that, I should say that already we know the expression of probability of error of BPSK. That is half of error complementary function in the bracket root of EB by N naught. That expression already we have discussed, but how that expression is coming from which kind of derivations are required for that. Okay, that we will discuss today because these things are in module 2. Okay, GSOP and this kind of probability of error calculation, these things are in module 2. Okay, and in module 4, we are directly writing the expression of probability of error of any digital modulation techniques. So whatever it is, today we are going to see how the probability of error calculation is to be done by taking one example of BPSK. Okay, so we are considering BPSK here. This is the this block is nothing but the receiver block, receiver section block. This is received signal. Sorry. This is transmitted signal. This is transmitting through the channel. Some noise is added. YT is received at the receiver side. That means this portion is actually RX, receiver section. This is your transmitter section, and this is your channel section. Okay. So this signal is received, multiplied by phi 1t because of it is coherent or synchronous detection, then passing through some integrator, and finally we are getting the value of y. Okay. Finally, we are getting the value of y. Y is nothing but the observation. Y is nothing but some observation. Okay. And these two things together known as correlator or correlation receiver or synchronous receiver or synchronous detection. Whatever, all the things are same actually. Now, very interestingly, we will say for the case of BPSK that I is 1 and 2. Okay, that means whenever x1, that means that time we are considering that bit 1 is present. Whenever x2, we are considering that bit 0 is present. Whenever bit 1 is present, that is denoted by this one. We know this thing. Bit 0 is represented by this one. We know this thing also. This is nothing but the BPSK concept. BPSK signal is passing through the channel. Definitely some noise will be added. Here we are considering the noise is additive white Gaussian noise. Additive white Gaussian noise. That noise is considered as additive white Gaussian noise. Okay. Different kinds of noise are there, and that we have to consider. Okay. So this noise is denoted by N, different kind of N, that is capital N you can say, and in which two things are there. One is the mean, one is the variance. Mean is 0 for AWGN channel. Variance is n naught by 2 is equals to sigma n square. N naught is the noise power. So these are the standard equation of AWGN channel, where mean is this, variance is this. Whatever the signal is transmitted, 1 or 0, whatever the signal is transmitted, these things are constant for AWGN channel. Now, that is the first concept. Next, YT. YT is actually this one, received. So what we are receiving? We are receiving X1 and or X2. X1 means bit 1, X2 means bit 0. That X1 and X2 added with some noise, and X1 and X2 we can write down in this way also, added with some noise. This is for bit 1, this is for bit 0. Now, this Y, which is actually your X1 and X2, that thing is actually YT. This YT, this one actually, is passing through some multiplier multiplied by phi 1t. So Y1 is multiplied by phi 1t, then some integrator, finally Y we are getting. This is Y. So don't get confused. YT is multiplied by phi 1t. YT is multiplied by phi 1t, passing through some integrator. That is why this integration we are doing. And finally we are getting Y. This is your Y. YT, this is YT, which is actually these values. Okay. Now what we will do? We will just put YT value, this one, for bit 1, or YT value, this one, for bit 0 in this equation here. So YT is your this expression. So I have written that expression out. This thing is nothing but your noise term denoted by N, which is having mean 0, variance N naught by 2. Root of EB, you take it out of the integration, and integration 0 to TB phi 1 t square dt is nothing but 1, because of it's an orthonormal function. Phi 1 is a basis function, which is an orthonormal function. So integration of phi 1 square t dt is 1. So finally what we will have? We have root of EB only. So root of EB plus the noise term for bit 1. Similarly for bit 0, if you put this one in this expression, we will get minus root of EB plus the noise term for bit 0. Just you put it and you'll get it like this. Okay, up to this. After that, mean of observation. What is the observation? Observation is denoted by Y, where Y present after the integration. See, this is your Y after the integration. So after the integration, we have Y. That is the observation. After integration, we have this Y, this Y. Okay, and that Y is nothing but the observation. So what is the mean of observation and variance of observation? These two things we have to find out. So mean of observation means denoted by, actually mean of observation is denoted by capital E in the bracket observation, or mu Y. Mu Y. This Y is nothing but either plus root of EB or minus root of EB, depending on bit 1 or 0 respectively, and mean of noise is 0. Mean of noise is 0. Okay. So mean of observation is now either root of EB or minus root. That means mu y is root of EB or minus root of EB depending on bit 1 or bit 0. That is the mean of observation. Same way, we will find out variance of observation. Here, just remember that mean of EB, EB is a constant term. So mean of EB is a constant term only. So that is coming. Minus root of EB. So minus root of EB is only coming. But mean of noise is 0. Mean of noise is 0. Okay. So this is the mean of observation. Now variance of observation. Formula is that expected value E in the bracket y minus y bar. Y bar is actually mean. This y bar is actually your mean of y or observation. Okay. And this y is the only observation. Y. So y is what? Root of EB plus n or minus root of EB plus n. Either of this. So if I am putting y as root of EB plus n for bit 1 minus mean of y or mean of observation, that is this one. So these two will be cancelled out. We will have E n square. This is nothing but the variance. Variance is your n naught by 2. Similarly, when 0 is the bit is transmitted for bit 0, this y is your observation, that is minus root of EB plus n naught, sorry, plus n. This y for bit 0 will be minus root of EB plus n minus mean of y. Mean of y means minus EB, so it will be plus of this. So now this will be cancelled out. Again n square E or E n square is there. So this is nothing but the variance denoted by n naught by 2. So this is the variance expression. So whatever the bit is, 1 or 0, variance value is same. And mean value is this. Remember, this is the mean value. This is the variance value of the observation y after the integration in the receiver section block diagram. That is the conclusion. For this case, just you have to remember mean how to calculate and variance how to calculate. And this y is nothing but the observation. Observation y is what actually? Observation y is after the integration, whatever we are getting, this is the y. So this y is nothing but this one for bit 1. This y is nothing but this one for bit 0. Now mean of y means mean of this and mean of this, that is your this one. Variance of y, using this expression, we will have n naught by 2 only for 1, for 0 both. So this is the conclusion of this part. Now, interesting thing is that probability density function. Probability density function, PDF of Gaussian random variable. PDF of Gaussian random variable. This is the expression. This is the expression. Don't be afraid of it. This is one expression of Gaussian random variable where f of capital X, which is the random variable. In our case, it will be your observation, capital Y. This is the capital Y. A small x, which will be your small y. Okay. So capital thing is your random variable and a small thing is your values that capital X takes. this is your variance. This mu is your actually mean. I have mentioned here. So this is the definition of Gaussian PDF, probability density function of Gaussian random variable, in which these are the parameters. In which these are the parameters. Okay. Now, next class we will start from here. Today here I am stopping.